In this video lab report, I will be discussing my observations of a falling object at increasing velocity in the real world. I will also be walking through the methods of observation and data analysis I used to compare real-world physics to that of a computer model I created using VPython. In short, I'll be discussing how the concept of a change in velocity, acceleration, and Newton's second law can be seen in the world around us, as well as a computer's perfect situation. Finally, I'll go over possible discrepancies between my observed data and a computer model, as well as the what if and what does it mean lab questions. This will inform how I obtain the ultimate conclusion that Newton's second law is upheld by my observations and the rigorous testing by the computer model. To begin my observations, I recorded a tennis ball being dropped from a set distance. Note that when the tennis ball was dropped, it began its path with a velocity of 0. I then imported the video into Tracker and used it to analyze what I'd video recorded. I set up Tracker, including changing the axis so that what was originally the positive x-axis was rotated to the negative y-axis. I also set the origin at the ball's starting point to ensure accurate readings. Then I used Tracker to record data about the tennis ball's location in regard to time. As you can see in the video, the velocity of the ball increases as time passes, so there is a positive acceleration present. You will later see in the presentation, in the final graph of my observations, that the gradually increasing slope of the ball's position versus time data describes a non-zero net force on the ball or system, in essence, an acceleration. Next, I used VPython to set up a computer model of the tennis ball to eventually compare real-world physics to the computer's data. In Python, I had to write two sets of code, one with no drag, or just the force of gravity, and one with turbulent drag, or gravity and drag together. In both codes, I set the mass of the tennis ball to be a recorded 0.057 kilograms. Next, I set the initial position vector from Tracker to be 0, negative 0.0010 meters. The ball's initial velocity was also set to 0, 0, 0, since it starts from rest. Time also starts at t is equal to 0 seconds. This is where the changes in the code come into play. In the no drag code, there's obviously no drag. In the turbulent drag code, however, the magnitude of drag, or B, is set to 0.035 newtons to match the observed results of the Tracker data. In the while loops, the loop repeats until t is equal to 0.733 seconds. Next, the no drag code has the weight force and F net forces set. In the turbulent drag code, the equation for turbulent drag is added and is thus changed slightly. Following this, the ball's velocity and position are set. Finally, the arrow scale for the turbulent drag code is added, as well as code to govern the changes in the arrows to show how gravity and drag affect each other. After running the codes, I took the data points in a CSV file and plugged them into a Microsoft Excel sheet to compare with the Tracker data. Using this data, I created a chart comparing the Tracker, no drag, and drag included data of the tennis ball. As the graph shows, the Tracker data and the computer with drag data are approximately the same, while the computer model without drag is vastly different. This should be expected because the non-drag model only considers gravity, so there is no force to counteract it. All three graphs do show an increase in velocity, or increase in slope of the graph. This also shows, via Newton's second law, that there is a positive acceleration. In essence, this means that there is a non-zero net force. As for the possible errors in my observations that could have caused the discrepancies in the graph, sleight of hand while releasing the ball, and the blurred effect on the ball in the slowed Tracker video come to mind. Also, the ball may not have been falling perfectly along the y-axis in the video. Fixing these possible errors could give more accurate and cohesive results. So what does it all mean? The answer to this question is that the computer model does predict a terminal velocity, meaning that the slope of the graph ceases to change. This means that there is a net force of 0 acting on the ball, and the forces of drag and gravity cancel each other out. The Tracker data may predict a terminal velocity shown, but more data points and time are needed. The computer model without drag does not predict terminal velocity because there's no drag to cancel out gravity. What about the what if question? If the tennis ball was thrown instead of let go, it'd still have the same terminal velocity because drag and gravity would eventually cancel out. This is assuming no other forces are acting on the ball. However, the amount of time for terminal velocity to be reached depends on how hard the ball is thrown. This is confirmed by the new computer model and Excel graph I made where the initial velocity is not 0. In conclusion, the Tracker data is supported by the computer model. When an object is dropped from a set distance when gravity and drag are the only acting forces, the object experiences initial acceleration and eventually terminal velocity, and a non-zero net force. In a nutshell, as stated before, Newton's second law is upheld.